Each atom inside your body originated in a star that detonated before our solar system took shape. The carbon threaded through your cells, the oxygen filling your lungs, the iron coursing through your blood, all manufactured inside nuclear furnaces across billions of years. You were constructed by this cosmos from the fabric of this cosmos. The constants permitting atoms to form and stars to ignite occupy values so exact that nudging any single one would yield a universe holding absolutely nothing. If that thought grabs hold of you, hit subscribe, because today we confront the question no one prepared you for. What if the universe is not a container you inhabit, but a living system you already belong to? And the most disturbing evidence has been sitting in the open the whole time. The laws governing everything you have ever perceived, touched, or contemplated fit onto one sheet of mathematics. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force. 4. Interactions, a small collection of constants defining their intensities. Every star that has ever blazed, every atom that has ever assembled, every pulse that has ever beaten operates on these 4 forces and nothing beyond them. You might anticipate that a cosmos as diverse and intricate as ours would demand elaborate mechanisms, thousands of specific instructions, endless exceptions and workarounds. Instead, it operates on equations brief enough to print on a T-shirt, governed by a parameter list shorter than a shopping receipt. And the remarkable thing is not the brevity. The remarkable thing is that the settings appear tuned with near impossible accuracy to allow stars rather than drifting gas, chemistry rather than inert matter, minds rather than emptiness. Alter any fundamental constant by even a small fraction, in several cases by less than 1%, and you do not end up with a different kind of universe. You end up with no universe whatsoever, not something alien, just featureless nothing dilating in silence forever. Physicists call this the fine-tuning problem. It ranks among the most profound unsolved mysteries across all of science, positioned at the threshold between what can be detected and what can be accounted for. The precise values of the fundamental constants appear exquisitely optimized for complexity. Gravity must be forceful enough to compress gas into stars, but feeble enough at the atomic scale to permit stable atoms. The nuclear force must be powerful enough to unite nuclei, but not so powerful that all hydrogen fused in the opening seconds after the Big Bang. The energy yield of nuclear fusion must occupy a narrow band that allows stars to shine consistently across billions of years. The cosmological constant, the energy threaded through empty space, must remain small enough that the universe does not expand too quickly for gravity to ever build structures. The concentration of matter in the early universe must have been balanced against the expansion velocity to extraordinary exactness. Each constant is individually restricted. Together, they construct a web of mutual dependencies, all simultaneously fulfilled in a manner that produces atoms, chemistry, planets, and minds. The likelihood of this occurring through chance in the standard sense of the word is not merely small. It is effectively zero. What renders this situation authentically baffling, rather than simply odd, is that physicists did not choose these constants. They measured them. The constants are inputs fed into our equations, not results that emerge from them. No deeper framework derives their magnitudes. They appear, as best current physics can determine, to be genuinely unconstrained parameters. They could have taken different values. The universe might have possessed a different gravitational constant, a different nuclear force, a different fusion efficiency. As far as we understand, nothing forbids it. And if the constants could have differed, then the fact that they hold precisely the values enabling our existence is a fact demanding an account. That account is not supplied by any framework in the current catalog of science. The gap between the precision of the observation and the absence of any explanation constitutes the problem. It is not dissolving, and it is the launch pad for the most extreme propositions in modern cosmology. The ratio of gravity to electromagnetism is among the most arresting quantities in physics. Gravity is weaker than electromagnetism by a factor of roughly 1 followed by 36 zeros. This enormous disparity is not an artifact of how forces are defined. It is a physical reality with sweeping consequences. At the scale of individual particles, gravity is essentially irrelevant. It is so feeble that it contributes nothing to the forces binding atoms or propelling chemical reactions. Electromagnetic forces command the microscopic domain, pinning electrons in orbit around nuclei, governing chemical bonds, dictating the architecture of everything from elementary molecules to elaborate proteins. But gravity compounds with mass. As matter accumulates, gravity intensifies. A planet carries enough mass that gravity sculpts its form and binds its atmosphere. A star contains enough mass that gravity squeezes its core to the temperatures and pressures where nuclear ignition occurs. Galaxies and their clusters are bound by gravity, acting across spans where electromagnetism has become negligible. The precise ratio of the two forces draws the dividing line between the microscopic domain, ruled by electromagnetism, and the macroscopic domain, ruled by gravity. Shift it, and stellar physics transforms fundamentally. Amplify gravity relative to electromagnetism, and stars combust 1,000,000 times faster, depleting their fuel in thousands of years rather than billions, leaving no window for planets to assemble or chemistry to develop. Diminish gravity, and the threshold for stellar ignition climbs too high. Gas clouds never compress to the temperatures where fusion begins, and no star ever lights. The strong nuclear force has its own tolerance window. It binds protons and neutrons inside atomic nuclei against the electromagnetic repulsion between positively charged protons. Its magnitude relative to other forces dictates which elements can exist. If the strong force were roughly 2% weaker, the deuteron, a proton joined to a neutron, the initial step in hydrogen fusion, would be unstable. Stellar fusion would cease entirely. The cosmos would remain hydrogen forever. If the strong force were several percent stronger, the diproton, two protons fused together, would be stable, and fusion in stars would proceed far too rapidly, consuming all available hydrogen almost at once. The universe would burn fiercely for a brief instant, and then descend into permanent cold darkness. Both failure modes are absolute. Our strong force sits between these extremes, not near the boundary of the viable range, but comfortably within it, permitting stable nuclei for the first 92 elements, allowing stellar fusion to proceed steadily across billions of years, enabling the accumulation of chemical complexity that ultimately yields everything. For the initial density of matter in the early universe, the required precision is at minimum 1 part in 10 to the 60th power. Had the density been fractionally greater relative to the expansion rate, gravity would have conquered expansion, and the cosmos would have recollapsed before a single star found time to form. Had it been fractionally less, matter would have dispersed so swiftly that gravity could never have gathered it into structures. The universe commenced its existence balanced on a point so exact that writing the precision in standard notation demands more digits than most humans have ever contemplated in their lifetimes. This is not philosophical abstraction. It is a derivation based on the measured properties of the cosmos, a consequence of the equations of general relativity applied to the initial conditions. The universe began in an extraordinarily ordered state, one that permits the very lengthy, very structured history it has undergone. And we have no explanation for why. In the 1950s, Fred Hoyle sat down to work through the mathematics of carbon formation inside stars. Hoyle was among the most brilliant and combative scientists of his era, a man who had spent years disputing religious and mystical readings of cosmology, who coined the phrase Big Bang as a derisive mockery of what he viewed as a simplistic theory. He was not seeking evidence of design. He was trying to solve a technical puzzle in nuclear astrophysics. The problem was this: carbon assembles inside stellar cores when 3 helium nuclei collide and merge into a single carbon nucleus. This procedure is called the triple alpha reaction, and it is what separates a universe of hydrogen and helium from a universe with a periodic table. The difficulty is that 3-body simultaneous collisions are extraordinarily improbable, even inside the compressed, energetic interior of a star where encounters occur constantly. By straightforward probability, the triple alpha reaction should be far too sluggish to generate the carbon abundance we detect. The mathematics and the observable reality were completely at odds. We exist. We consist of carbon. The universe holds vast quantities of carbon-based chemistry. The naive calculation insists this should be impossible. Hoyle resolved this through a deduction that many physicists still find startling. For carbon to assemble efficiently, the carbon nucleus must possess a quantum mechanical resonance, a precise energy state located at a very specific energy level. This resonance would function as a funnel for the triple alpha reaction, dramatically elevating the probability that a collision produces a stable carbon nucleus rather than immediate disintegration. Without the resonance, the reaction is negligible. With it, carbon accumulates efficiently inside stellar cores across millions of years, eventually scattered into space when the stars expire, seeding the interstellar medium with the foundation of chemistry. Hoyle calculated exactly where the resonance energy would have to fall. He accomplished this using no knowledge of atomic physics. He drew on one observation: that complex chemistry exists, that carbon is abundant, that we are present. He published the prediction. Physicists in laboratories measured the relevant energy state of the carbon nucleus. The resonance was precisely where Hoyle's argument from our existence required it to be. Not approximately, exactly. A specific quantum property of the carbon atom had been precisely calibrated to make carbon production efficient inside stellar cores. Nothing in the theory of atomic nuclei at that time predicted this resonance. Nothing suggested it would occupy that specific energy level. Hoyle derived it by reasoning backward from the bare fact of our existence, and the universe had done precisely what was required. Hoyle spent years unsettled by this. He wrote that the cosmos appeared to have been arranged by a superintelligence. He did not intend this theologically. He was among the least religious scientists of his generation. He meant it as a characterization of improbability. The carbon resonance is not like a coincidence in the conventional meaning of the word. It is not like a striking card draw or an improbable encounter. It is a precisely calibrated quantum mechanical property of the carbon nucleus, sitting at a value derivable only from the observation that chemistry is possible. Remove it, and the universe holds no carbon, no organic molecules, nothing from which life as we recognize it could emerge. It exists, and no physical theory has explained why it holds the specific value it does. A physicist named Lee Smolin examined the fine-tuning problem and identified something nobody had articulated in quite the same way. The problem looked recognizable, not from physics, but from biology. Before Darwin, biologists confronted a problem structurally analogous to fine-tuning. Organisms appeared exquisitely suited to their environments. The eye was ideally designed for vision, the wing for flight, the gill for underwater respiration. Every structure appeared calibrated for its function with a precision that seemed to necessitate intentional design. The only account that seemed coherent to most people was that an intelligence had fashioned each organism for its purpose. Darwin demonstrated this was wrong. Adaptation can emerge from a blind, undirected process. Random, heritable variation acted upon by differential reproductive success, repeated across many generations. No intelligence required, no intention required, simply variation, differential reproduction, and time. Smolin asked whether the same reasoning could extend to universes. Could the constants be what they are? Not because they were designed or randomly selected, but because universes bearing these constants generate more descendants than universes with different constants. And could black holes be the reproductive mechanism by which universes propagate? The proposal is called cosmological natural selection, and it proceeds as follows. When a massive star collapses into a black hole, the interior reaches extreme densities, where the equations of general relativity cease to function. In several approaches to quantum gravity, particularly loop quantum gravity, the collapse does not terminate in a singularity but rebounds. Matter is compressed to the maximum density quantum spacetime can sustain and then springs outward, generating a new region of spacetime expanding away from the collapse point. This new region is causally severed from the parent universe. It expands into its own history. It possesses its own timeline. From the eye perspective of anything existing within it, it would appear exactly like a new universe launching from a hot, dense initial state, a new Big Bang. If this is accurate, the constants of the offspring universe are not identical to those of the parent. They are inherited with minor, random variations. Most variations are detrimental. They yield universes with fewer stars, fewer black holes, diminished structural complexity. But occasional variations amplify black hole production. Universes with such variations leave more offspring. Their constants propagate through the population of universes. Across many generations, the multiverse, the aggregate of all universes, comes to be dominated by those with constants approaching optimal black hole production. Our universe, as one member of this population, should carry constants near that optimum. The critical and elegant connection is that the constants maximizing black hole production also maximize everything else we observe. Black holes demand massive stars. Massive stars require the nuclear force at its specific value, strong enough for stellar fusion, restrained enough not to consume all hydrogen immediately. That same nuclear force at that same value enables the stellar nucleosynthesis of heavy elements. Heavy elements enable chemistry. Chemistry enables biology. A universe optimized through blind reproductive selection for black holes ends up, as a necessary side consequence of that optimization, being compatible with atoms, molecules, planets, and minds. You are not the aim of the selection. You are the collateral complexity, the byproduct of the cosmos's extended reproductive history. There is a location in our galaxy where something is occurring that our physics cannot describe. This is a technical statement, not a theatrical one. At the center of every black hole, according to the equations of general relativity, there exists a singularity, a point where matter is compressed to infinite density, where space-time, curvature is infinite, where every relevant physical quantity diverges toward infinity, and the equations stop yielding coherent results. Physicists do not believe singularities genuinely exist in nature. When a theory generates infinities in physical quantities, it signals that the theory has exceeded its domain of validity. The singularity is not a feature of reality. It is an admission by the theory that it has reached the boundary of what it can characterize. For decades, physicists presumed the singularity would eventually be resolved by a superior theory, a quantum theory of gravity uniting general relativity with quantum mechanics. The unified framework would supplant the singularity with something finite and describable, presumably something extreme but not fundamentally impenetrable. This was the operating assumption. The singularity was a provisional placeholder marking the site of something real that an improved theory would eventually illuminate. The specific replacement that several rigorous approaches to quantum gravity propose is extraordinary. In loop quantum gravity, one of the two leading contenders for a quantum theory of gravity, space and time, are not continuous at the smallest scales. They possess a minimum unit of extent called the Planck length, below which the concept of distance loses its meaning. When matter is compressed toward a black hole singularity, it approaches the Planck density, the maximum concentration the quantum structure of spacetime can sustain. At that threshold, the quantum pressure of discrete spacetime resists. The collapse does not proceed to a singularity. It bounces. Matter reaches peak compression and then begins expanding outward. The bounce does not return matter to our own universe. The interior of a black hole is causally severed from its exterior. Nothing can traverse from inside the event horizon back outward by definition of what an event horizon is. The bounce generates a new region of spacetime expanding outward from the point of maximum compression, entirely disconnected from our own. A new spacetime, a new cosmic chronicle. From the perspective of anything that might exist inside this new region, it would resemble the early universe as we perceive it, an initial state of extreme heat and density, expanding and cooling with all the subsequent phases of structural formation, star formation, and everything that follows still lying ahead. The event horizon is not a physical membrane. You cannot stand upon it or touch it. It is a geometric boundary in space-time, the sphere within which the curvature of space-time is so extreme that all possible trajectories point inward. An observer plunging through the event horizon of a large black hole would detect nothing unusual at the moment of crossing. No alarms, no physical sensation. The horizon is not a location where physics transforms dramatically from one side to the other. It is simply the threshold beyond which communication with the external universe becomes permanently impossible. Once inside, the future leads inevitably toward the extreme densities at the core, and if loop quantum gravity is correct, toward a bounce into somewhere entirely new. Our galaxy harbors roughly 100 million black holes. The majority are stellar mass black holes, the collapsed remains of massive stars that erupted in supernovae billions of years ago. Their masses span from a few times the mass of our own star to perhaps 50 or 60 times that figure. They drift through the galaxy in silence, interacting with their environment only through gravity, invisible except when they draw in nearby matter, and that material glows as it descends. There are also neutron stars in comparable numbers, the remnants of stars not quite massive enough to collapse into black holes. And at the galactic center sits a supermassive black hole with a mass roughly 4 million times that of our own star. The galaxy is populated with black holes at every scale. The observable universe contains somewhere between 100 billion and 2 trillion galaxies. Each galaxy carries its own population of stellar mass black holes, its own chronicle of supernova and stellar deaths, its own central supermassive black hole. The total number of black holes in the observable universe is a figure requiring scientific notation to express something on the order of 10 to the 18th power, possibly larger. Each of those objects is, if cosmological natural selection is correct, a potential universe birth event. The collapse of each one either terminated in a singularity or rebounded into a new universe. If even a fraction of them bounced, the number of universes generated by our single observable universe is incomprehensibly vast. Now extend this across time. The observable universe has been generating black holes since the first massive stars perished roughly 100 million years after the Big Bang. That was more than 13 billion years ago. Black holes have been forming continuously ever since. The rate has fluctuated. It was elevated when the star formation rate was higher in the first several billion years, and has diminished as the cosmos aged and its gas supply was consumed by successive rounds of star formation. But the total inventory accumulated over 13 billion years is enormous. Extend it further. If each new universe generated inside a black hole proceeds to form its own stars, its own black holes, its own reproductive events, the multiverse implied by cosmological natural selection is more than large. It is recursively boundless. Universes generating universes generating universes in a branching structure that has been operating for however long the entire process has been running, which may be far longer than our own universe's 14 billion years. Our universe is one node in a genealogical tree of cosmic reproduction, extending back toward some ancestral universe and forward toward all the progeny being generated right now inside every black hole currently collapsing in every galaxy visible in the sky above us. This scale transforms the framing of the fine-tuning problem entirely. It is no longer asking why our universe has constants compatible with complexity. It becomes, given a population of universes that has been evolving through reproductive selection across an immense span of time, is it remarkable that we find ourselves in one positioned near the optimum for black hole production? By the logic of natural selection, the answer is no. We would expect precisely this. The constants that appear improbably calibrated for complexity are neither coincidence nor design. They are the anticipated outcome of the process. They are what success looks like in a competition that has been running longer than we can grasp. Stars are the universe's metabolic engines. They take in hydrogen, the lightest, most elementary element produced in vast quantities during the Big Bang, and they combust it. Nuclear fusion in stellar cores converts hydrogen into helium, releasing energy as light and heat at a rate so immense that a single star radiates more energy in 1 second than the entirety of human civilization has consumed across all of history. The process is gradual by stellar timescales. A star resembling our own will burn hydrogen steadily for roughly 10 billion years before its fuel diminishes. But across those 10 billion years, it performs an extraordinary transmutation. It converts the lightest and most plentiful element in the cosmos into the heavier elements that enable complex chemistry. When hydrogen runs low in a stellar core, the star does not simply cease. Gravity compresses the helium-rich core, elevating its temperature until helium itself begins fusing into carbon and oxygen, the backbone atoms of organic chemistry. More massive stars proceed further, fusing carbon into progressively heavier elements in a cascade of shells, each layer combusting a denser fuel until an iron core occupies the center. Iron marks the terminus of exothermic stellar fusion. When an iron core assembles, the nuclear burning that has sustained the star against gravity abruptly halts, and the star implodes in milliseconds. The outer layers crash inward, rebound from the hardening core, and detonate outward in a supernova. Supernovae are the cosmos's most consequential chemical events. The explosion disperses into the surrounding interstellar medium all the elements forged throughout the star's existence: the carbon, oxygen, nitrogen, silicon, and iron, along with additional elements synthesized in the blast itself under the extreme conditions of the shock front. A single supernova scatters into space a mass of heavy elements exceeding the mass of our entire star. That enriched material mixes with surrounding gas. The following generation of stars and planets assembles from this enriched mixture. Each cycle of stellar birth and death adds to the chemical complexity of the interstellar medium, building from the simplicity of hydrogen and helium toward the richness of a periodic table with 92 naturally occurring elements. This cycling of matter through stellar processes is metabolism in the literal meaning of the word. Energy is extracted from the gravitational potential of collapsing gas, converted through nuclear processes into electromagnetic radiation, and emitted into space. The byproducts, heavy elements, are not waste but feedstock for the next cycle. Each generation of stars inherits the chemical legacy of the generation before it. The process is cumulative and directional. It advances from simplicity toward complexity, from a cosmos of hydrogen toward a cosmos of carbon-based chemistry, driven not by any purpose but by the specific physics of nuclear forces and gravity operating jointly across billions of years. The universe is constructing the preconditions for chemistry, not because it intends to, but because the machinery it runs on contains that consequence as a built-in implication. The first generation of stars that emerged in the early universe would be unrecognizable to a contemporary astronomer. They assembled from pure hydrogen and helium, the only elements present in the universe before stellar nucleosynthesis had completed even one generation. Without heavier elements in the gas, without the carbon, oxygen, and other elements that modern molecular clouds contain, the cooling mechanisms that permit gas to condense into small stars resembling our own were entirely absent. The gas clouds condensing in the youthful universe collapsed into objects of extraordinary mass, hundreds of times the mass of our own star, burning with an intensity and brevity that gave them no opportunity to be gentle about it. These primordial stars burned at surface temperatures so extreme they radiated primarily in the ultraviolet, emitting intensely at wavelengths capable of ionizing hydrogen. The radiation from this first generation of stars ionized the neutral hydrogen that had pervaded the universe since the cosmic microwave background was released, carving ionized plasma bubbles around each star. As additional stars ignited, the bubbles expanded and merged, and the universe transitioned from the opacity of neutral gas to the transparency of ionized plasma, a phase called the epoch of reionization, occurring roughly 1 billion years after the Big Bang. The universe we observe today, pervaded by transparent intergalactic gas and the light of billions of galaxies, is the consequence of that transition. The first stars perished violently and rapidly. Their enormous masses meant they consumed their fuel within a few million years, a cosmically brief span compared to the billions of years that subsequent smaller stars would achieve. When they collapsed, the supernovae they produced were of unprecedented energy, dispersing enormous quantities of heavy elements into the surrounding gas. Some of the most massive first stars may have collapsed directly into black holes, so massive that they did not fully explode but instead swallowed themselves, leaving behind nothing but gravity. But many did erupt, and those explosions represented the first dispersal of heavy elements in the history of the cosmos. The second generation of stars that assembled from the enriched gas was fundamentally distinct. Heavier elements radiate energy much more efficiently than hydrogen, permitting gas to cool to lower temperatures before collapsing. This meant the second-generation gas clouds could condense into smaller, denser entities, stars more closely resembling those we observe today, including some within the mass range where stars burn for billions rather than millions of years. Around some of those second-generation stars, the heavy elements dispersed by the first generation gathered gravitationally and built up solid bodies. Planets formed. For the first occasion in cosmic history, there existed stable surfaces, liquid water within temperature ranges compatible with complex chemistry, and the chemical building blocks required for biological processes. The universe was building toward something, not because it harbored intentions, but because the particular physics of stellar evolution carries that consequence when allowed to operate long enough. In the first fraction of a second following the Big Bang, within a time interval so fleeting that no analogy in ordinary experience captures its brevity, the universe underwent a phase of exponential expansion called cosmic inflation. Space itself enlarged at a rate vastly surpassing the speed of light. The distance between every pair of points in the universe doubled, then doubled again, then doubled again, over a duration so abbreviated that even the most rapid atomic processes are glacially slow by comparison. A region of space smaller than any particle we have ever detected expanded during that interval to something approximately the size of a piece of fruit. And the energy powering this expansion, stored in a hypothetical quantum field called the inflaton, eventually decayed, converting into the particles that became everything in the observable universe. Why did inflation occur? The leading response involves the inflaton field, which permeated early spacetime with an enormous energy density that propelled the exponential expansion. When the inflaton decayed, when it descended from its high-energy configuration to a lower one, inflation concluded, and the released energy became photons, quarks, leptons, and eventually every particle in the cosmos. But this is a description, not an explanation. We do not know why the inflaton existed, where it originated, or what it is at a fundamental level. It is a hypothetical construct inferred from its consequences. Inflation is supported by compelling observational evidence, but its mechanism remains unknown. The evidence is persuasive because inflation accounts for several otherwise inexplicable features of the cosmos. The cosmic microwave background is nearly perfectly uniform in temperature across the entire sky. including regions that were never in causal contact according to the standard non-inflationary picture. Before inflation, the entire observable universe was enclosed within a tiny region compact enough for thermal equilibrium to establish itself. Inflation then stretched this equilibrated region to the dimensions of the observable universe, carrying its uniformity along with it. The flatness of space, the fact that the geometry of the universe is neither positively curved like a sphere, nor negatively curved like a saddle, but precisely flat, is also explained by inflation, which stretches any initial curvature toward flatness, the way a wrinkled balloon smooths as you inflate it. And the scale invariant spectrum of density fluctuations that seeded all structure in the universe matches the predictions of inflationary models with precision. But inflation carries a troubling implication. In quantum mechanics, fields decay through quantum fluctuations locally, not uniformly. The inflaton decayed in our region. Inflation concluded here, and our universe emerged. In the vast regions surrounding our bubble, the inflaton had not yet decayed. Inflation persisted there, and continues still, generating new decay events and new bubble universes in an endless cascade. This is eternal inflation. Our universe is one bubble within an infinite, ever-expanding sea of bubble universes, each forming at a different moment, each expanding into its own vast history, each causally isolated from every other. The geometry of space-time guarantees we can never perceive any of the other bubbles. Their light can never reach us. We are separated by distance and also by the architecture of space-time itself. Whether those other bubbles share the same physical constants as ours, or carry different ones, is a question whose answer would determine whether the fine-tuning problem has a natural resolution or remains mysterious. When astronomers constructed the first large three-dimensional maps of the cosmos in the 1980s and 90s, surveys spanning millions of galaxies across volumes measuring hundreds of millions of light-years, the picture that emerged was not what anyone had anticipated. Galaxies were not scattered randomly. They were not distributed uniformly. They were arranged in an intricate three-dimensional web of filaments and sheets surrounding vast, nearly empty voids. Galaxy clusters occupied the nodes where filaments intersected. Sheets of galaxies formed the walls between voids. The voids themselves extended for hundreds of millions of light-years containing virtually nothing. A few isolated galaxies, but overwhelmingly empty space. This structure, the cosmic web, is the largest organized architecture known to exist. It spans scales at which entire galaxies resemble specks of dust. It was not engineered. It emerged over billions of years from the interplay of gravity and the density fluctuations seeded by inflation. Marginally denser regions attracted more dark matter, which attracted more ordinary matter, which drew in still more dark matter in a feedback cycle operating for billions of years, accumulating mass into filaments and nodes while leaving the intervening regions increasingly vacant. The specific pattern of the web encodes information about the initial density fluctuations, the ratio of dark matter to ordinary matter, and the expansion history. Cosmologists study it the way geologists examine rock strata, as an archive of the forces that shaped the cosmos. What renders the cosmic web remarkable beyond its scale is a statistical correspondence that has attracted serious scientific attention. When researchers compared the quantitative properties of the cosmic web with the quantitative properties of the neuronal network of the human brain, measuring such things as the distribution of connection intensities, the clustering of adjacent nodes, and the ratio of dense clusters to empty voids, They identified specific, measurable statistical resemblances. Two systems, separated in scale by roughly 27 orders of magnitude, exhibited comparable network statistics. The researchers were careful not to overclaim. The similarity does not imply the universe is conscious. It does not imply the brain is cosmological. It means the same mathematical principles of network self-organization appear to operate across scales spanning from neurons to galaxy clusters. This is actually less surprising at first glance and more interesting on reflection. Both the brain's neuronal network and the cosmic web arise from a constrained set of organizing principles. A large number of nodes linked by pathways, with growth of new connections governed by local interactions, producing hierarchical clustering and efficient long-range communication across time. These are very general properties of self-organizing networks. The same principles generate similar statistical signatures regardless of the physical substrate. What is genuinely interesting is that the universe's self-organization, driven by gravity and dark matter, produces network statistics resembling those generated by biological evolution and neural development. The cosmos builds networks according to the same abstract rules at every scale it has organized. Nobody possesses a complete explanation for why. The anthropic principle was given precise formulation by physicist Brandon Carter in the 1970s, though the underlying concept is considerably older. In its weak form, it states simply that we can only observe a universe compatible with our existence. If the universe lacked properties permitting observers, there would be no observers to remark upon the fact. This sounds like a truism, and in one sense it is, but it carries a non-trivial implication that required time to appreciate. The anthropic principle is sometimes deployed to explain fine-tuning. Why do the constants hold values permitting observers? Because if they did not, no one would be present to observe them. This explanation is logically valid. It is also profoundly unsatisfying to many physicists, because it does not account for why a universe with observer-compatible constants exists at all. It only establishes that if any observer-compatible universe exists, the observers within it will observe observer-compatible constants. What it fails to explain is why at least one such universe should exist. For the anthropic explanation to accomplish genuine explanatory work, you require a large ensemble of universes carrying varying constants, sufficient in number that it is unsurprising at least one of them is compatible with observers. Without the ensemble, the anthropic principle explains nothing. With an ensemble, whether the string landscape or the bubble, universes of eternal inflation, the anthropic principle becomes a genuine probabilistic argument. If there are vastly many universes with differing constants, and if the distribution of constants across those universes is broad enough to encompass our values, then finding ourselves in a universe with our constants is not surprising. We are a sample drawn from the distribution, and we necessarily occupy a compatible region of it. The argument functions. The difficulty is that it functions too effectively. An explanation accounting for why our universe has any set of observer-compatible constants, regardless of which specific set, is an explanation making no particular predictions. It predicts only that we find ourselves in some universe permitting observers. Every feature of our universe extending beyond mere compatibility with observers, the specific value of the nuclear force, the specific density of dark matter, the specific geometry of the cosmic web, is left without account. Thus, the anthropic principle combined with a large ensemble is less an explanation than a framework justifying why no specific explanation is necessary. Whether that is satisfactory depends on whether one believes science should explain particular features of our cosmos or merely demonstrate that some observer-compatible universe is possible. Smoline's cosmological natural selection claims to accomplish more by proposing a definite mechanism, selection for black hole production. It predicts not merely that we exist, but also that our constants fall near the optimum for a specific physical process. This represents a prediction beyond anything the anthropic principle alone can generate. Whether it constitutes the correct explanation, whether the selection mechanism is real, whether the constants genuinely sit near the optimum for black hole production, these are questions open to investigation even if the investigation is technically demanding. And that distinction between an explanation, generating specific testable predictions, and one merely demonstrating that existence is possible, lies at the heart of the ongoing debate between the string landscape and cosmological natural selection, driving theoretical cosmology today. The first generation of stars that ignited in the young cosmos burned within a universe utterly unlike our own. The cosmos was roughly 100 million years old, still dark in most regions, still cooling from the primordial fireball. Neutral hydrogen and helium filled the gaps between sparse concentrations of dark matter that had been slowly gathering under gravity. There was no carbon, no oxygen, no nitrogen, no iron, none of the heavy elements that modern molecular clouds contain, because heavy elements are forged inside stars, and no stars had yet expired. The absence of these heavier elements meant the gas could not shed energy as efficiently as it does today. Cooling is what permits gas to compress into dense entities. Without efficient cooling, only very massive clouds of gas could collapse under their own gravity, and they condensed into very massive stars. The first stars were behemoths. Their masses ranged from tens to possibly thousands of times the mass of our own star depending on local conditions. They burned at temperatures so extreme their surfaces radiated principally in the ultraviolet, emitting light at wavelengths energetic enough to ionize surrounding hydrogen gas. Each massive star carved a bubble of ionized plasma in the encircling neutral hydrogen. And, as more stars formed, these bubbles expanded, coalesced, and eventually saturated the entire universe with ionized intergalactic gas. This process, called cosmic reionization, transformed the cosmos from opaque to transparent for the second time in its history, the first being the formation of neutral atoms that produced the cosmic microwave background. The reionized universe we observe today, transparent and pervaded by the light of billions of galaxies, is a direct consequence of the radiation emitted by this first generation of stars. Those pioneering stars lived briefly and perished violently. Their extraordinary masses meant their fusion proceeded at a furious pace, exhausting fuel within a few million years. By comparison, a star like our own burns steadily for 10 billion years. When the first stars depleted their fuel, their cores collapsed, and they detonated in supernovae of unprecedented violence. Some were so massive they may have collapsed entirely into black holes, contributing to the inaugural generation of stellar mass black holes. Others exploded and distributed into the surrounding gas the first heavy elements the cosmos had ever witnessed: carbon, oxygen, nitrogen, magnesium, silicon, iron. That dispersal was the first step in assembling the chemical complexity that ultimately produces chemistry, biology, and minds. The second generation of stars condensing from the enriched remnants of the first was fundamentally transformed. The introduction of heavy elements gave the gas new pathways to shed energy. Carbon, in particular, is an excellent coolant at the temperatures where star-forming clouds collapse. Gas enriched with even trace quantities of carbon could cool more effectively, enabling smaller and more stable clouds to condense. The second generation encompassed stars across a broader range of masses, including some resembling our own star, modest, long-lived, stable objects capable of burning for billions of years. Around some of those stars, the heavy elements scattered by the first generation gathered gravitationally and built up solid bodies. Planets formed for the first time. The cosmos was not merely expanding and cooling. It was building toward something. Consciousness is something the universe unambiguously produces. You are conscious, and you are assembled from the same atoms as everything else. Whatever consciousness represents at the physical level, it is a genuine phenomenon occurring in a universe whose fundamental laws, as we currently formulate them, make no reference to experience. The equations of quantum mechanics characterize particles and fields, and their interactions without mentioning what it is like to be anything. General relativity describes the curvature of spacetime without reference to subjective awareness. The standard model of particle physics offers a comprehensive account of the fundamental constituents of matter and their interactions. And it contains nothing corresponding to the feeling of perceiving red, or the sensation of hunger, or the sense that you exist and are having these thoughts. Yet you experience all of those things. The universe runs on physics that contains no mention of experience. And yet experience arises somewhere between the equations and the reality. Something is being omitted. And the question of what is being omitted, the question of why physical processes generate subjective experience at all, is the hardest problem in science. Not the most challenging, unsolved problem in a particular discipline. The most challenging problem across all of science, the one with the least progress and the most fundamental implications. Neuroscience can map the correlates of consciousness in extraordinary detail. It can identify which brain regions activate during different types of experience, which neural oscillations accompany awareness, what befalls brain activity under anesthesia or dreamless sleep. These correlates are real and informative. But identifying the physical activity correlating with consciousness is not the same as explaining why that activity generates consciousness. You can chart every neural circuit involved in the experience of perceiving blue, and still have no account of why those circuits produce a qualitative experience of blue, rather than simply an information processing configuration that responds to blue wavelengths. The gap between the physical description and the experiential reality is, as far as current theory extends, unbridgeable. Panpsychism is among the oldest and also among the most recently revived philosophical positions on consciousness. It holds that consciousness is not manufactured by matter at some threshold of complexity, but is fundamental to matter at every level. Electrons do not possess rich experiences with emotional content, but they have some most primitive variant of what might be called interiority, some minimal responsiveness that is not merely mechanical. At higher levels of organization, this primitive property compounds into progressively more elaborate forms. Human consciousness is what this foundational property looks like when organized into a system of roughly 100 billion neurons with trillions of synaptic connections, extensive feedback loops, and the capacity for recursive self-modeling. The hard problem of consciousness dissolves on this view, not because it is resolved, but because its foundational premise that consciousness must be generated from something that is itself not conscious is rejected. For most of the 20th century, panpsychism was dismissed as obviously mistaken. In the last 2 decades, it has re-entered serious philosophical and even scientific discussion, partly because the hard problem has proven so thoroughly resistant to conventional approaches, and partly because a rigorous mathematical framework, integrated information theory, has furnished it with a basis for generating specific predictions. Integrated information theory was developed by neuroscientist Giulio Tononi, originally as an attempt to understand consciousness in terms that could be measured and tested rather than simply characterized philosophically. The theory's central quantity is phi, a number measuring how much information a system generates as a whole beyond what its constituent parts generate independently. A system with phi greater than 0 is, according to the theory, conscious to some extent. A system with phi equal to 0 has no experience. The larger the phi, the more expansive and intricate the conscious experience. To grasp what phi signifies, consider 2 contrasting examples. A camera is a large array of light-sensitive elements, each registering the brightness at one point in an image. The elements are largely independent. Each pixel reports its value without complex interaction with the others. The complete camera does not generate much information beyond what the aggregate of its pixels generates. Phi is low. The camera has, according to integrated information theory, essentially no experience. A human brain, by contrast, is a massively interconnected system where every region influences every other. The visual cortex transmits information to the prefrontal cortex, which feeds back to the visual cortex, which connects to memory systems, which link to emotional centers, which modulate attention, which in turn shapes visual processing. The whole generates information that could not be predicted from any subset of its parts. Phi is very high. According to integrated information theory, this elevated phi corresponds to the rich conscious experience of being a person. The framework generates specific predictions about which physical systems should be conscious. A brain region during dreamless sleep has lower phi than during alert wakefulness, consistent with the reduced or absent experience during deep sleep. The theory predicts that gradually severing connections between brain regions should reduce phi and correspondingly diminish conscious experience. It predicts that certain apparently complex systems, very large but modular systems with comparatively little internal integration, will have low phi and little or no consciousness. These predictions are in principle testable, and some have been examined with results that Tononi and colleagues regard as supportive. The most potent objection to integrated information theory is also the most vivid. The computer scientist Scott Aaronson demonstrated that the theory implies certain very simple computational systems, large arrays of logic gates performing particular types of computation, could carry very high phi, and therefore, on the theory's account, a rich conscious experience. This strikes most people as intuitively wrong. Logic gates are not undergoing experiences. Spreadsheets computing thousands of cells simultaneously are not conscious. Aronson's objection points toward a potentially deep flaw in the theory. Tononi's responses have partially addressed the objection, but not fully resolved it. The theory remains contested among physicists, neuroscientists, and philosophers of mind. But whatever the ultimate fate of integrated information theory, it accomplishes something significant that prior approaches did not. It provides a mathematical framework for asking whether any physical system is conscious, and it generates specific predictions about the properties distinguishing conscious from non-conscious physical systems. Applied to the cosmos, it raises a question that had previously been purely metaphorical. Given the deep integration of the universe as a physical system, the gravitational connections between all its constituents, the pervasive cosmic microwave background, the quantum entanglements extending across its entire history, does the universe possess phi? Is there, in the most primitive possible sense, something it is like to be the universe? The candid answer is that the calculation has not been executed, and the framework is disputed. But the question no longer sits entirely outside the domain of science. For the first 380,000 years following the Big Bang, the universe was opaque. Not dark, but opaque. The distinction is significant. The universe was saturated with an extraordinarily hot plasma, a dense fog of protons, electrons, and photons in constant interaction. Photons could not travel far in this plasma before colliding with an electron and being absorbed and re-emitted. Light was imprisoned in the plasma, the way light is trapped inside a thick fog bank, perpetually scattered, incapable of traveling freely in any direction. The universe blazed in every direction, but nothing could be seen through it. Every line of sight vanished into the glow of the surrounding plasma within a short distance. This plasma-opaque phase persisted for 380,000 years. The cosmos expanded and cooled throughout this interval. When the temperature descended to roughly 3,000 degrees, hot enough to liquefy steel many times over but cool by cosmic standards, a transition occurred. At this temperature, electrons had decelerated sufficiently to be captured by protons and form neutral hydrogen atoms. Neutral atoms do not interact with photons the way free electrons do. The plasma abruptly became a gas of neutral atoms, and the photons that had been confined within it were released to travel unimpeded for the first time. The universe became transparent in what amounts to a geological instant. Those photons are still traversing space today. They have been crossing the cosmos for more than 13 billion years and arrive at our detectors from every direction simultaneously. The expansion of the universe has stretched their wavelengths from the high-energy visible and near-infrared of a gas at 3,000 degrees to the low-energy microwave frequencies they carry today. We call this the cosmic microwave background. It is the universe's most ancient light, a portrait of conditions when the cosmos was 380,000 years old. And it is one of the most information-rich objects in observational cosmology. Every direction in the sky radiates at microwave frequencies at nearly identical temperatures, about 2.7 degrees above absolute zero. The uniformity is extraordinary, 1 part in 100,000. But embedded within that uniformity are minute variations. The cosmic microwave background is not perfectly uniform. It possesses warm regions and cool regions, slightly denser and slightly less dense zones at the level of 1 part in 100,000. These infinitesimal temperature fluctuations are the impressions of quantum fluctuations in the inflaton field, stretched to cosmic scales during inflation. They are the seeds from which all structure in the universe germinated. Every galaxy, every star, every planet traces its ancestry to a temperature fluctuation in the cosmic microwave background, a quantum ripple in the universe's earliest history, stretched to cosmic scale and then amplified across billions of years by gravity into the intricate structures we observe today. 380,000 years after the Big Bang, the cosmos was a nearly uniform gas of neutral hydrogen and helium with minute density fluctuations, the 1 in 100,000 variations imprinted in the cosmic microwave background. From that almost featureless point of departure, gravity spent the ensuing several billion years constructing everything. The process was not swift by human reckoning, but it was inexorable. Gravity does not rest. Every region, even marginally denser than its surroundings, attracted additional matter. Additional matter increased density further. The feedback was positive. Denser regions grew denser. Emptier regions grew emptier across millions and then billions of years. Dark matter was the principal actor in this process. Dark matter does not interact with light or with ordinary matter except gravitationally. It does not emit, absorb, or deflect photons, but it responds to gravity and generates gravitational attraction. In the early cosmos, when ordinary matter remained coupled to the photon gas, still exchanging energy with the radiation filling the plasma, dark matter was free to begin clustering. It started forming the first gravitational structures, before ordinary matter could, constructing invisible scaffolding into which ordinary matter would later fall. The first large-scale structures in the cosmos were dark matter halos, gravitational wells in the distribution of dark matter, not yet containing any ordinary matter, simply concentrated regions of gravitational potential waiting to be populated. When ordinary matter decoupled from the photon gas at recombination, when the universe became transparent, it began to fall into the dark matter scaffolding. Gas flowed along dark matter filaments, accumulating at the intersections. In the densest intersections, the gas achieved sufficient density and temperature for nuclear fusion to ignite. The first stars appeared. Then the first small galaxies assembled around those initial stars. Then larger galaxies formed as smaller ones merged and accumulated additional gas. The process built hierarchically from small to large across hundreds of millions to billions of years, producing the galaxy-scale structures we observe today, embedded within dark matter halos containing 10 to 100 times as much dark matter mass as stellar mass. The product of this multi-billion-year process is the cosmic web, the intricate three-dimensional network of galaxy filaments and voids constituting the large-scale structure of the universe. Every galaxy visible in the night sky resides within a dark matter halo. Every galaxy cluster sits at the convergence of dark matter filaments. The voids between filaments are largely empty. Most matter has been swept into the filaments and nodes across billions of years of gravitational accumulation. The cosmos has organized itself from near-perfect uniformity into a complex architecture spanning hundreds of millions of light-years, driven by nothing beyond gravity, acting on a slightly uneven distribution of matter seeded by quantum fluctuations in the first fraction of a second after the Big Bang. The scale of the organization is extraordinary. The mechanism is elegantly simple. Dark matter is among the most firmly established realities in modern cosmology. The evidence for its existence is overwhelming, drawn from multiple, entirely independent observations, all pointing toward the same conclusion. And dark matter is simultaneously one of the most embarrassing mysteries in physics. We know it is present. We know roughly how much of it exists. We know how it is distributed. We cannot determine what it consists of. The first compelling evidence for dark matter emerged from the rotation curves of galaxies. When astronomers measure the velocities at which stars orbit the center of a galaxy at various distances from that center, they anticipate finding a pattern analogous to our solar system. Objects farther from the center orbit more slowly, just as the outer planets orbit more slowly than the inner ones. This is what Newtonian gravity predicts for a mass concentration near the center. But galaxies do not behave this way. Stars in the outer regions of galaxies orbit at approximately the same velocity as stars near the center, regardless of their radial distance. The rotation curve remains flat where it should decline. The only way to reconcile this with gravity, as we comprehend it, is to suppose that a vast halo of invisible mass encircles every galaxy, providing additional gravitational pull to maintain the outer stars at their observed velocities. Independent confirmation derives from gravitational lensing. When light from a distant object traverses the vicinity of a massive foreground object, the mass deflects the light's path. Gravitational lensing predicted by general relativity and confirmed to high precision. By measuring how significantly a galaxy cluster distorts the light of more distant background galaxies, astronomers can compute the total mass of the cluster. The answer is consistently far greater than the mass in visible stars and gas. Somewhere between 5 and 10 times as much mass is present as the visible material can account for. That surplus mass is dark matter. The formation of cosmic structure furnishes a third line of evidence. Constructing the observed cosmic web from the minute density fluctuations in the early universe demands a component of matter that can begin clustering before ordinary matter does, and that furnishes the gravitational scaffolding for ordinary matter to fall into. Dark matter, which does not interact with the photon gas in the early cosmos and can therefore begin clustering early, provides this scaffolding perfectly. Models of cosmic structure formation, incorporating dark matter in the observed quantities, reproduce the observed cosmic web with great precision. Models lacking dark matter do not. Despite this overwhelming evidence for dark matter's presence, no experiment has directly detected a dark matter particle. Detectors sunk deep underground to reduce the cosmic ray interference, searching for the rare collision of a dark matter particle with an atomic nucleus, have found nothing. Particle accelerators energetic enough to manufacture dark matter particles, if the most popular theoretical models are accurate, have found nothing. Gamma-ray observations hunting for the energetic photons that dark matter self-annihilation would produce have detected no convincing signal. The most theoretically favored dark matter candidates have been progressively eliminated at the parameter values where they were expected to emerge. Dark matter, whatever it ultimately is, has proven more elusive than our best theories anticipated. In the late 1990s, 2 independent teams of astronomers were measuring distances to remote supernovae. These explosions, produced when aging stars detonate after accumulating excessive mass, possess a reliably consistent peak luminosity, making them useful as cosmic distance markers. By measuring how bright a distant supernova appears, one can calculate how far away it lies. By measuring how rapidly the galaxy containing the supernova is receding from us, one can gauge how fast the universe was expanding when the supernova's light was emitted. Comparing distances and recession velocities at different epochs allows scientists to track how the expansion has evolved across time. Both teams expected to uncover evidence of the expansion slowing down. The universe is full of matter, and matter gravitates. Gravity should be drawing things together, working against the expansion, causing it to decelerate with time. The question was how much deceleration, not whether deceleration existed. Both teams prepared to measure the rate of slowdown. What they discovered was that distant supernovae were dimmer than expected, farther away than they would be in a decelerating cosmos. The universe was not decelerating. It was accelerating. The expansion was proceeding faster at late epochs than at early ones. Something was pushing space apart with amplifying force, opposing gravity at large scales and driving the universe to expand more rapidly as time advanced. Both teams initially suspected systematic errors. The result was so unanticipated that neither group trusted it enough to publish without exhaustive verification. They examined their calibrations, their distance measurements, their observational methods. The result held. In 1998, both groups published their findings. The expansion of the universe was accelerating. The discovery earned its lead authors the Nobel Prize in Physics in 2011. The force driving this acceleration is called dark energy. It constitutes roughly 68% of the total energy content of the cosmos. Ordinary matter, everything you can see, touch, or detect by any means, amounts to approximately 5%. Dark matter accounts for roughly 27%. The dominant component of the universe, the force actively reshaping its geometry and determining its ultimate fate, is completely uncharacterized in its fundamental nature. We know it exists because of what it produces. It accelerates the expansion. We do not know what it is. The theoretical candidate for dark energy is the cosmological constant, a fixed energy density associated with empty space representing the energy of quantum vacuum fluctuations. Einstein introduced the cosmological constant, then discarded it. Then the universe proved to require it after all. The difficulty is that quantum field theory predicts a vacuum energy density roughly 10 to the 120th power larger than what observations require. This is the cosmological constant problem, the largest discrepancy between theory and observation in all of science. Either something cancels the quantum vacuum energy with near-perfect precision to 1 part in 10 to the 120th through a mechanism entirely unknown, or our theory of vacuum energy is wrong in a way we have not yet identified. Both possibilities demand fundamental revisions to our understanding. Dark energy is not an asterisk. It is a signal that something about our deepest theories of nature is profoundly mistaken. Physics rests on two extraordinary foundations. Quantum mechanics describes the behavior of everything at subatomic scales with an accuracy that is, without exaggeration, the most precisely verified framework in the history of science. The predictions of quantum electrodynamics, the quantum theory of electromagnetism, have been tested to 12 decimal places. General relativity characterizes gravity and the large-scale structure of space-time, and has been confirmed with equivalent precision at the scales where it applies. The orbits of planets, the bending of light by massive objects, the gravitational waves from colliding black holes, both theories are triumphs of human comprehension. Both are extraordinarily accurate, and they are fundamentally incompatible with each other. The incompatibility is not a practical concern in most circumstances. Quantum mechanics governs the very small. General relativity governs the very large. In the middle range where most physics operates, the two theories rarely need to communicate. Atoms are too small for general relativity to matter. Galaxies are too vast for quantum mechanics to matter. In the everyday world, you can employ one theory or the other depending on the scale of the problem, and never encounter the conflict. The conflict becomes genuine and inescapable in two circumstances: the extreme densities at the center of a black hole and the extreme conditions of the very early universe. Both situations involve matter compressed to densities at which the quantum effects of space-time itself become consequential, where gravity is sufficiently powerful that quantum mechanics cannot ignore it, and quantum effects are significant enough that gravity cannot ignore them. These are the domains where a unified theory, a quantum theory of gravity, is indispensable, and where neither quantum mechanics nor general relativity, applied separately or combined naively, generates coherent answers. The black hole singularity is the most vivid illustration of where the conflict matters. General relativity predicts a singularity. Quantum mechanics carries a principle, unitarity, asserting that information is never destroyed. If the singularity obliterates information about matter that fell into the black hole, quantum mechanics is violated. If information is somehow preserved, general relativity's characterization of the black hole interior must be wrong. Both possibilities demand revising one of our most successful theories. The information paradox is not merely a technical puzzle. It is a signal that our current understanding of physics is fundamentally incomplete at the intersection of its two finest theories. The pursuit of a quantum theory of gravity is one of the central challenges of contemporary theoretical physics. Loop quantum gravity and string theory are the two leading approaches, and they generate different predictions about the physics of black hole interiors, the resolution of singularities, and the character of space and time at the smallest scales. Loop quantum gravity predicts that singularities are supplanted by quantum bounces, the mechanism potentially enabling cosmic reproduction in Smolin's model. String theory predicts that the black hole interior is connected to the exterior through the holographic principle, with information on the event horizon encoding everything inside. Both predictions are in principle observable, if only we could observe the interior of a black hole. We cannot. The resolution of the information paradox and the correct theory of quantum gravity remain unknown. The multiverse arising from eternal inflation is not a speculative appendage to inflationary cosmology. It is an almost unavoidable consequence of the physics that makes inflation function. Understanding why requires understanding what inflation is and how it terminates. Inflation is driven by a scalar field, the inflaton, in a high-energy state. The field carries a potential energy propelling the exponential expansion of space. As the field descends its potential, shedding energy, inflation decelerates and eventually ends. In our region of the universe, the inflaton reached a low-energy state roughly 10 to the negative 32nd power of a second after the Big Bang. Inflation concluded. The energy released became the particles filling the universe. All of this is standard inflationary cosmology corroborated by observations. The complication arises from quantum mechanics. In quantum field theory, fields do not change uniformly everywhere. They fluctuate. Quantum fluctuations in the inflaton field can, in certain regions, push the field back up its potential rather than allowing it to descend. In those regions, inflation persists rather than concluding. The probability of such a quantum fluctuation is small within any given region. But inflation is expanding the volume of the inflating region exponentially. New volume is being generated faster than inflation ends in any particular small region. The total volume still inflating grows exponentially without bound. Once started, inflation generates new inflationary volume faster than it loses inflationary volume to bubble formation. It never ceases globally. This is eternal inflation, and it implies that our universe, our bubble, is one among an infinite, ever-expanding collection of bubbles. Each forms when the inflaton decays locally, each expands into its own vast cosmic history. Each remains forever causally isolated from every other. The bubbles are not arranged spatially like soap bubbles in foam. They are separated by regions of still inflating space that are themselves expanding faster than light. No signal from any bubble can reach any other. Each bubble is, from the inside, an entire universe with its own past, its own future, its own physical laws. Whether the physical laws differ from bubble to bubble depends on the structure of the inflaton potential. Specifically, whether the inflaton can settle into different low-energy states in different bubbles, each corresponding to different effective physical constants. In the context of string theory, which predicts an enormous landscape of possible low-energy states, the answer is yes. Different bubbles land on different points in the landscape and acquire different physical constants. In the context of other inflationary models, the constants might be identical in every bubble. The distinction matters enormously for explaining fine-tuning. If constants vary across bubbles, the anthropic landscape explanation succeeds. If they do not, fine-tuning remains unaccounted for, and Smolin's natural selection becomes more significant. The string theory landscape emerged from an unexpected development in the history of string theory. String theory was originally devised in the hope that it would derive a unique set of physical constants, that the mathematical consistency requirements of a theory of vibrating strings would compel a specific set of particle masses, force intensities, and other parameters. The expectation was that the theory would explain why the constants hold the values they do by demonstrating they could be nothing else. Instead, string theory revealed an enormous space of possible solutions. The extra dimensions string theory requires beyond the three spatial dimensions we experience can be compactified in an astronomically large number of configurations. Each configuration yields different effective physics in the three large dimensions we inhabit. The number of possible configurations is roughly 10 to the 500th power. This collection of possible solutions is the landscape. Rather than predicting a unique set of constants, string theory predicts that all possible sets of constants compatible with the theory's mathematical structure are realized somewhere. The universe we observe corresponds to one specific configuration of the extra dimensions. But nothing within the theory singles out our configuration as privileged. Every configuration is equally valid from the theory's perspective. This was initially perceived as a catastrophe for string theory, evidence that the framework was too expansive to be predictive. Physicist Leonard Susskind reframed it as a solution to fine-tuning. If there is an enormous landscape of possible physics and eternal inflation generates a universe exploring every point in that landscape, then the question of why our universe has its specific constants carries the same answer as the question of why a particular lottery ticket was drawn. With enough tickets, every number eventually appears. We occupy a bubble that happened to land on constants compatible with our existence. Given the vastness of the landscape, it is essentially guaranteed that some bubbles are compatible with observers. We find ourselves in one because we cannot be in any other. The response from Lee Smolin and others was pointed. The landscape, combined with the anthropic principle, explains why we exist but predicts nothing about which specific constants we should observe. There are presumably many distinct configurations compatible with the existence of observers, each with somewhat different constants. Without knowing the probability distribution of constants across the landscape, which requires understanding the details of the landscape measure problem, an unsolved technical challenge in string theory. The landscape cannot specify which observer-compatible configuration we should expect to inhabit. The theory is consistent with any set of observer-compatible constants. It makes no prediction distinguishing our constants from any other compatible set. Smolin argues this means the landscape as an explanation is vacuous. It accounts for the existence of observers, but explains nothing specific about the universe those observers actually inhabit. Suskind's counter is that generating predictions about which set of compatible constants we should expect requires resolving the measure problem, and that the measure problem, while unsolved, is in principle solvable. A resolved measure problem might identify specific regions of the landscape as more probable, yielding specific predictions about constants. Until the measure problem is solved, the landscape remains an incomplete explanation, but not a meaningless one. The debate persists, and its resolution, if it comes, may demand observational evidence that current experiments cannot supply. Lee Smolin and Leonard Susskind embody two of the most carefully considered positions on one of the deepest questions in physics. Both acknowledge that the constants are finely tuned. Both accept that a multiverse of some variety is probably implicated in the explanation. They disagree fundamentally on what an adequate explanation should resemble and how science should proceed when the objects of explanation, other universes, are in principle unobservable. Susskind's position is essentially that the string landscape combined with eternal inflation represents the best available explanation for fine-tuning. It derives from our most advanced mathematics. It is consistent with all observations and renders the fine-tuning problem tractable by supplying a framework in which it is unsurprising that our cosmos is compatible with life. Susskind acknowledges that the theory does not predict which set of compatible constants we should expect. He regards this as a temporary limitation, not a permanent one. As string theory matures and the measure problem is better characterized, more specific predictions may become possible. Smolin's position is that a theory incapable of making specific testable predictions is not practicing science in the sense that has made science so generative. The defining feature of a sound, scientific theory is that it rules things out, that it predicts certain observations rather than others, that it is in principle capable of being wrong. A theory consistent with any observer-compatible universe, including any set of observer-compatible constants, rules nothing out. It is immune to falsification in a way that should disquiet scientists. Smolin contends that cosmological natural selection, despite its own gaps and uncertainties, is more scientifically valuable because it makes definite predictions. Our constants should sit near the optimum for black hole production. This prediction is checkable. The theory can be wrong. And that vulnerability to being wrong is, Smolin argues, what separates science from philosophy. The deeper issue concerns what it means for something to be explained. Suskind's landscape says the constants are explained by their position in an ensemble where every compatible configuration exists. The explanation is structural. Given the landscape, it is unsurprising that some configurations are compatible with observers, and we occupy one. Smolin's natural selection says the constants are explained by their genealogy. They are what they are because universes carrying these constants reproduced more successfully than universes with different constants. The explanation is historical. The constants hold the values they hold because they were victors in a competition that has been running longer than we can imagine. Both forms of explanation appear within science. Population genetics explains the frequencies of genetic variants partly structurally. Given a gene pool, some distributions are more probable, and partly historically, The present distribution reflects the particular history of selective pressures acting on this lineage. Both forms can be valid. The question is, which applies to universes? Answering that question requires either resolving the landscape measure problem or testing the predictions of cosmological natural selection, challenges that will occupy physicists for generations. Every structure in the universe exists because of a fundamental tension between entropy and gravity. Entropy is the tendency of energy to spread uniformly, of disorder to intensify, of concentrated things to scatter. Gravity is the tendency of matter to concentrate, to draw toward itself, to amass into dense objects. Between these two opposing tendencies, entropy pushing outward and gravity pulling inward, all interesting things happen. Stars burn because they are concentrations of matter seated in a gravitational well, dissipating an energy gradient between their scorching interiors and the frigid void surrounding them. As long as the gradient endures, as long as the core is hot enough to fuse elements and the surrounding space is cold enough to absorb the radiation, the star shines. Life sustains itself by continuously harvesting energy from an external source, deploying it to construct and maintain local order against the global increase of entropy. A living cell is more organized than the chemicals from which it formed. But the process constructing the cell generates more entropy elsewhere, in the heat it releases and the waste products it produces. Life is an entropy pump, creating local order at the cost of global disorder, sustained by an energy flow that cannot persist forever. The second law of thermodynamics asserts that entropy always increases in a closed system. This is the deepest statement about the direction of time in all of physics. The past is the direction of lower entropy. The future is the direction of higher entropy. You remember the past but not the future because the past corresponds to states of lower entropy, and the second law ensures entropy only ever climbs. Heat flows from hot to cold, never the reverse. Shattered cups do not spontaneously reassemble. Chemical reactions proceed in the direction of greater disorder. Everything we observe about the direction of time is a consequence of this single law. The universe commenced at the Big Bang in a state of extraordinarily low entropy. This is not obvious. The Big Bang was hot and dense, conditions we typically associate with disorder. But the relevant entropy is gravitational entropy, and a smooth, uniform distribution of matter represents a low entropy state from the gravitational standpoint. When you permit gravity to act on a smooth distribution, it generates clumping, dense regions drawing in matter, while empty regions become emptier. That clumping is an increase in gravitational entropy. The formation of stars, galaxies, and galaxy clusters represents the cosmos transitioning from a smooth, low-entropy state to a lumpy, high-entropy one. And the universe has been executing this transition for 14 billion years, with enormous quantities of low-entropy capacity still remaining to be claimed. The low entropy of the Big Bang is one of the most profound, unexplained facts in cosmology. Physicist Roger Penrose computed the probability of the universe commencing in a state as ordered as it appears to have been. The result is a number so tiny that writing it out would require more digits than there are atoms in the observable universe. The initial conditions of the cosmos were not merely improbable. They were improbable in a way that renders every other improbability in science look routine. Why the universe originated in such an ordered state, and whether this connects to the fine-tuning problem, remains unknown. It may be that the same mechanism setting the constants also determines the initial entropy, or It may represent a separate enigma requiring a separate account. Either way, it is among the most profound puzzles we carry. The far future of the universe follows from thermodynamics with logical inevitability. It unfolds in chapters, each darker and longer than the preceding one, and the final chapter endures forever. The first chapter to close will be the age of stars. The most massive stars already burned out billions of years ago. Stars of intermediate mass, like our own, burn steadily for billions of years, and then expand into red giants, expelling their outer layers and leaving behind cooling white dwarf cores. The smallest stars, red dwarfs, which constitute roughly 3/4 of all stars in the galaxy, burn so gradually and so efficiently that some will still be fusing hydrogen roughly 10 trillion years from now. 10 trillion years. The current age of the universe is roughly 14 billion years. The last red dwarf will outlive our present epoch by a factor of approximately 700. When the final star extinguishes, the galaxy will not go dark instantly. It will dim across immense timescales as the stellar remnants cool. White dwarfs radiate heat for trillions of years, fading gradually from white to yellow to red to invisible. Neutron stars cool similarly. Black holes, which accumulate matter but also radiate through the Hawking process, persist far longer. Stellar mass black holes evaporate on timescales of roughly 10 to the 67th years. Supermassive black holes evaporate on timescales of 10 to the 92nd years. These are figures that dwarf even the stellar cooling timescales by factors admitting no useful comparison in ordinary language. If protons decay, as many extensions of the Standard Model predict, though none have been confirmed, ordinary matter dissolves. Planets, asteroids, and white dwarfs over a timescale of roughly 10 to the 37th years would see every proton in every fragment of ordinary matter decay into lighter particles and radiation. The solid substance of the cosmos dissolves into a diffuse haze. What persists are black holes and the products of proton decay, photons, electrons, positrons, and neutrinos dispersed through an ever-expanding universe. The last black holes evaporate through Hawking radiation over timescales of 10 to the 92nd to 1,000th years. When they are gone, the cosmos holds nothing but an ever-diluting vapor of photons, neutrinos, and possibly electrons and positrons, expanding through an ever larger spacetime. Every photon redshifts to longer and longer wavelengths, carrying progressively less energy. Every temperature asymptotes toward absolute zero. Every density asymptotes toward zero. The universe achieves maximum entropy, featureless, uniform, thermally dead. This is heat death, and it is as near to nothing as something can become. Not fire and detonation, but stillness and uniformity, spread across timescales so vast that all of current cosmic history registers as a rounding error. You inhabit the brief, luminous middle chapter of a story that began with the Big Bang and concludes with featureless nothing. The chapter you are in, the Age of Stars, is extraordinarily improbable because it demands the specific initial conditions the cosmos happened to possess, and it is finite because entropy is perpetually increasing. The remarkable part of the story is unfolding now. You are within it. Stephen Hawking's discovery in 1974 that black holes are not black, that they emit radiation and gradually evaporate, stands among the most celebrated results in theoretical physics. It arose from applying quantum field theory to the curved spacetime surrounding a black hole and encountering something nobody had anticipated. Virtual particle pairs generated by quantum fluctuations near the event horizon could separate, with one particle escaping and its partner falling inward. The escaping particle carries energy away from the black hole, and repeated across an immense span of time, this process causes the black hole to lose mass. A black hole with the mass of our own star would require roughly 10 to the 67th years to evaporate entirely. But evaporate it will. This result transformed how physicists conceived of black holes fundamentally. Black holes were no longer permanent structures. They possessed a lifetime. They possessed a temperature, the Hawking temperature, inversely proportional to the black hole's mass, so infinitesimal for large black holes as to be immeasurable in practice but genuine and calculable in principle. And they possessed an entropy, the Bekenstein-Hawking entropy, proportional to the area of the event horizon in Planck units. The entropy of a black hole is the maximum possible entropy for a region of space of that scale. A black hole is the most disordered, highest entropy entity that can fit within its own boundary. This connection between black holes, thermodynamics, and quantum mechanics hinted that all three are deeply interrelated in ways we do not yet fully grasp. The difficulty Hawking radiation introduces is the information paradox. When matter forms a black hole, the information characterizing the precise quantum state of that matter, every particle's position, momentum, spin, and every other quantum attribute, descends with it into the interior. When the black hole evaporates, the Hawking radiation appears to be purely thermal. It is characterized entirely by the black hole's temperature, which depends only on its mass. It does not appear to encode any information about what fell in. If a book is swallowed by a black hole and the black hole evaporates, the book's contents appear to have vanished forever. Quantum mechanics insists this cannot occur. Information in quantum mechanics is always conserved in principle. The information paradox asserts it was not. Resolving the paradox requires either accepting that quantum mechanics is mistaken about information conservation in the presence of black holes, or accepting that general relativity is wrong about the characterization of the black hole interior, or identifying some mechanism by which information is encoded in the Hawking radiation so subtly as to appear thermal. Recent work has advanced toward the third possibility using tools from quantum, information theory, and holographic concepts from string theory. Specifically, a relation called the island formula that appears to restore unitarity. But the mechanism is deeply exotic, potentially demanding that the interior of a black hole is in some sense continuous with its exterior, that the geometry of spacetime near an evaporating black hole differs more radically from what classical general relativity describes than anyone had suspected. The information paradox remains unresolved, and its resolution may constitute one of the most consequential discoveries in theoretical physics of the coming century. Among the most significant and underappreciated concepts in science is emergence. Emergence is the principle that systems of interacting components can manifest behaviors and properties absent from the individual components and impossible to predict from the behavior of those components considered alone. Water is wet. Hydrogen and oxygen are not wet. The wetness of water is an emergent property. It arises from the collective behavior of water molecules and exists in none of them individually. Life is organized chemistry. No individual chemical reaction is alive. Life emerges from the coordinated interplay of many chemical reactions arranged in a specific structure. Consciousness is organized biology. No individual neuron is conscious. Consciousness, or something correlated with it, emerges from the coordinated activity of roughly 100 billion neurons arranged in a specific configuration. What renders emergence scientifically consequential is that it is hierarchical and cumulative. The cosmos began with quantum fields. Those fields, governed by quantum mechanical rules, produced particles. Particles, governed by quantum mechanical and electromagnetic rules, assembled into atoms. Atoms, following chemical rules derived from but not reducible to quantum mechanics, assembled into molecules. Molecules, following biochemical rules derived from but not reducible to chemistry, assembled into cells. Cells, following biological rules derived from but not reducible to biochemistry, assembled into organisms. Organisms, following ecological and evolutionary rules, developed nervous systems. Nervous systems, through processes still imperfectly understood, generated consciousness. At each level, something genuinely novel appears, and the novel thing depends on the level below, yet cannot be completely characterized in terms of the level below. This is what physicist Philip Anderson meant in his renowned 1972 essay when he argued that more is different. Anderson was addressing the view that all of science ultimately reduces to physics, that biology is merely applied chemistry, chemistry merely applied physics, and that with full knowledge of physics and all initial conditions, you could in principle anticipate everything. Anderson agreed with the first part. Everything is consistent with the laws of physics, but he argued that consistency is not the same as reducibility. Each new tier of organization generates concepts and laws that did not exist at the tier below, and cannot be derived from it without already knowing specifically what emerged. Temperature is a concept from statistical mechanics absent from Newtonian mechanics, even though temperature ultimately results from particles obeying Newtonian mechanics. Natural selection is a concept from biology absent from chemistry, even though evolution ultimately results from chemical processes. The universe's capacity for emergence is itself something that appears finely tuned. Most possible sets of physical laws would not generate emergence. They would yield universes where things interact, but never build toward complexity, where the energy gradients necessary to sustain organized structures do not exist, where the specific chemistry permitting self-replication is impossible. Our cosmos produces emergence at every scale. From chemical bonds to cosmic architecture, from individual cells to biospheres, from single neurons to conscious minds. The particular physics enabling this is the same physics that appears fine-tuned for complexity. The fine-tuning and the capacity for emergence are not independent properties of our universe. They are the same property viewed from different vantage points. James Lovelock's Gaia hypothesis, proposed in the 1970s, was initially received with skepticism so intense it was dismissed by many scientists before receiving serious consideration. The hypothesis stated that Earth's biosphere functions as a single self-regulating system, maintaining conditions favorable to life through complex feedback loops connecting biology, atmospheric chemistry, ocean chemistry, and geology. The oxygen content of the atmosphere, which has remained within life-compatible ranges for billions of years, despite massive inputs and outputs from geological and biological processes, provides one example. The mean surface temperature of the planet which has stayed within the range permitting liquid water despite a star that has brightened by approximately 30% over Earth's lifetime, a change that should have driven major temperature excursions, offers another. Lovelock's original framing employed intentional language that made scientists uneasy. He described the biosphere as wanting to maintain conditions, as though it pursued goals. Critics noted that biological systems do not pursue goals in any intentional sense. Natural selection generates feedback loops that happen to maintain certain conditions, not because the system aims to maintain them, but because the feedback loops doing so are self-reinforcing. They persist while less stable configurations dissolve. Lovelock eventually adopted more precise language, and the scientific core of the Gaia hypothesis that the biosphere exhibits large-scale regulatory feedback is now accepted as a productive framework for Earth system science, even if the word Gaia carries philosophical weight. Extend this principle carefully to the cosmos. A universe whose laws permit stable structures permits feedback loops. Feedback loops can sustain conditions within ranges that allow those feedback loops to continue. The universe's laws do permit stable structures. They permit structures that persist for billions of years, that develop internal models of their environment, that respond to their surroundings in ways maintaining their own existence. At every scale, from cells to ecosystems to planetary systems, the cosmos generates systems exhibiting self-regulation. Whether the universe as a whole exhibits self-regulation at the cosmic scale is a different and far harder question. One form of cosmic self-regulation is suggested by cosmological natural selection itself. If universes reproduce and constants are selected for black hole production, then the cosmos as a system possesses a mechanism maintaining certain properties, specifically the properties enabling black hole formation across generations. The selection pressure acts as feedback. Universes with constants generating many black holes leave many descendants, which inherit those constants, which generate many black holes, which leave many descendants. The feedback sustains the constants within a region of parameter space enabling complexity. This is self-regulation in a precise sense, operating on the multiverse rather than on any single universe, but self-regulation nonetheless. The question of what preceded the Big Bang has haunted cosmology since the Big Bang theory was established. It is a natural question, the kind children ask and adults learn to deflect. Time, as physicists comprehend it, is a feature of the universe. It began with or close to the beginning of the universe, and applying the concept of before to an era before time existed is potentially nonsensical. This is the standard response. It is logically coherent. It is also profoundly unsatisfying. Stephen Hawking and James Hartley proposed a mathematical framework for taking the unsatisfying answer seriously and exploring its implications. They called it the no-boundary proposal, and it constitutes a quantum cosmological description of the universe eliminating the need for an initial boundary condition. In their picture, the universe is described by a quantum mechanical wave function, a quantum state assigning probabilities to different possible cosmic histories. The wave function is defined on the space of all possible spacetime geometries and matter configurations, and obeys a quantum equation analogous to the Schrödinger equation of ordinary quantum mechanics. The defining feature of the no-boundary proposal is that the wave function assigns elevated probability to universes that are smooth and rounded at their smallest temporal scale. Universes possessing no boundary, no edge, no initial singularity. tracing a universe described by this wave function backward in time. The time dimension becomes progressively more spatial, until at the smallest scale it is indistinguishable from a spatial dimension. There is no first moment. Time does not commence at a boundary. The universe is a closed geometry in both space and time, finite but edgeless, like the surface of a sphere. Just as you can travel continuously across the surface of a sphere and never reach an edge, you can trace the universe's history backward continuously and never arrive at an absolute beginning. The implication is that the question of what happened before the Big Bang resembles asking what lies south of the South Pole. The question seems meaningful, but refers to something non-existent. Traveling further south from the South Pole does not lead to more southward territory. It leads back toward the north. Tracing further back in time from the Big Bang does not lead to an earlier moment. It leads to a geometry in which the concept of an earlier moment dissolves. The cosmos is self-contained. It requires no boundary condition imposed from outside. It simply exists, described by its wave function, which selects for smooth, round, finite geometries. The no-boundary proposal is beautiful mathematics and philosophically profound, but it does not fully satisfy the intuition that something must account for why there is a universe rather than nothing. Hawking explicitly addressed the question of why the universe exists, arguing that a cosmos described by the no-boundary wave function requires no external cause. It is self-contained. But this seems to many people to answer a mathematical question rather than the underlying philosophical one. Why does a universe governed by quantum mechanics exist at all? Why is there anything rather than nothing? The no-boundary proposal relocates the question rather than dissolving it. There is a simple and total fact about your situation that is easy to overlook because it is so absolute. You cannot depart the universe. There is no exterior. There is no boundary you can approach, cross, or gaze across. The universe is not a region of space with something else beyond it. It is everything. Every direction you can indicate leads to more universe. Every distance you can travel, however large, leads to more universe. The cosmos is not a container in which you reside. The cosmos is the totality of existence, and you are a constituent of it. This has a specific consequence for the project of comprehending the universe. Every instrument you use to study it is assembled from it. Every measurement you make deploys apparatus built from atoms governed by the same laws you are investigating. Every theory you formulate is expressed in a language shaped by the evolved cognitive architecture of a primate brain that itself emerged from the universe's own biological history. You cannot step outside and regard the whole from a neutral vantage. You are embedded in the subject of your own investigation, using tools derived from that subject, constrained by limitations that subject imposed. This is not cause for despair. It is an observation about the character of science. Science is not a view from nowhere, a perspective on reality observed from outside. Science is the cosmos doing something remarkable, organizing some of its matter into configurations capable of modeling the rest of it. When you practice physics, you are a physical system constructing a model of the physical system containing you. When you practice cosmology, you are a portion of the universe attempting to comprehend the whole. The project is not impossible. It has succeeded beyond anything that could reasonably have been anticipated. But its character is fundamentally self-referential. And that self-referentiality has implications for what can and cannot be known. Physicist John Wheeler, among the most inventive thinkers of 20th century physics, developed the concept of the participatory universe to capture this self-referential quality. Wheeler argued that observation is not merely passive recording, but active participation in constituting reality. In quantum mechanics, unobserved systems persist in superpositions. Observation collapses superpositions into definite outcomes. Wheeler extended this insight. The universe before the emergence of observers was not fully definite. The emergence of observers, entities capable of making quantum measurements, participates in crystallizing the past into its definite form. The universe brought forth observers, and observers participate in bringing forth the universe. The circle closes on itself. Most physicists regard this as excessively speculative, but Wheeler's participatory universe captures something genuine about the structure of the situation. You are not a passive observer of the cosmos. You are a constituent of it, a product of its evolution, a configuration of its matter capable of modeling its own origins. The universe is not simply there waiting to be observed. It produced the observers. And in producing the observers, it produced the only entities capable of noticing that it merits noticing. When you look at the night sky, truly look at it rather than merely glance, you are watching the universe observing itself. This is not a metaphor. It is a characterization of what is physically happening. Your eyes are optical instruments constructed from atoms forged in stars. The neurons processing the visual information are chemical computers running on physics established in the first seconds after the Big Bang. The consciousness contemplating the meaning of what you perceive is an emergent property of matter that has been organizing itself across 14 billion years. The sky returning your gaze through your eyes is the cosmos deploying the most intricate structures it has assembled to examine the structures surrounding it. The emergence of self-modeling systems, systems that contain representations of their own operation and employ those representations to pose questions about the whole, is arguably the most significant development in the universe's history. Not the Big Bang, not the ignition of the first star, not the formation of the first planet. Those were intermediate steps. The cosmos invested 14 billion years building toward complexity. And one of the things that complexity eventually yields is the capacity to examine itself. The first time a mind posed the question of why anything exists, the universe crossed a threshold that, as far as we know, had never been crossed before. This self-examination is more than philosophical reflection. It is productive. The last 4 centuries of science represent the cosmos comprehending with increasing precision and depth its own architecture. We know the laws governing matter at the subatomic scale. We know the structure of space-time. We know the history of the universe from the first fractions of a second after the Big Bang to the present moment. We know the process that forged the atoms in our bodies. We know the scale of the cosmos from the radius of an atomic nucleus to the radius of the observable universe, a span of roughly 62 orders of magnitude. Every one of those discoveries was the universe knowing more of itself through the specific physical process of having organized some of its matter into minds. The philosopher Blaise Pascal wrote in the 17th century that the universe's infinity terrified him. He was a man, a thinking reed, infinitely small within a vast, indifferent cosmos. But the thinking reed knew things the cosmos did not. Pascal's sense was that consciousness is fragile and diminutive against the scale of the physical universe. The contrary perspective is that consciousness is the universe's most extraordinary accomplishment. that the physical cosmos, boundless as it is, contains within it something the universe itself lacked for most of its history, the ability to comprehend it. You are not small within a large universe. You are the cosmos's most complex configuration of matter, executing the task it required 14 billion years to become capable of, knowing itself. Every cosmology eventually encounters the same wall. Follow any chain of causes sufficiently far backward, and you arrive at something possessing no prior cause within the framework you are using. The Big Bang emerged from initial conditions that are themselves unexplained. Eternal inflation operates from a prior state whose origin is unspecified. The no-boundary universe is self-contained, but does not explain why a self-contained quantum universe exists. Every framework ultimately bottoms out in a starting point it cannot derive from anything more fundamental. This is the origin question, and it is the one inquiry that no scientific theory has yet answered, and that may be genuinely beyond answering. The difficulty is not merely technical, it is conceptual. Every possible explanation for why the universe exists is itself a thing that exists and therefore demands explanation. If you account for the cosmos by citing a prior cause, the prior cause exists and requires an account. If you explain it by asserting mathematical necessity, that necessity is itself a thing that exists and requires explanation. If you maintain it has always existed, that eternal existence is a fact requiring explanation. Every proposed answer introduces something demanding its own account, regressing without terminus. Some philosophers have argued the question itself is malformed. The question of why there is something rather than nothing presupposes that nothingness is the default state, and that departing from it requires justification. But nothing, in the strict philosophical sense, is not a state from which something can depart. Nothing is not a vessel that can be empty. The concept of nothing may simply lack coherence when applied to the most fundamental level of reality. If nothing is not a coherent concept, then why there is something rather than nothing is not a coherent question. It only appears to pose something profound. In actuality, it asks why the cosmos is not something that cannot exist, a departure from a baseline possessing no coherent description. This is philosophically sophisticated, but feels evasive. The sense that something requires explanation, that the universe's existence is contingent, that matters could have been otherwise, seems irreducible. Even granting that nothing is incoherent, the intuition that the universe need not have existed, that its existence is a contingent rather than necessary fact, persists. Cosmological natural selection addresses this intuition by embedding our cosmos within a larger structure possessing its own history. But the larger structure also requires explanation. Loop quantum cosmologies posit a bouncing universe with a prior contracting phase that also requires explanation. The regress never concludes. The most candid statement available is this: we do not know why the I's universe exists. This is not a provisional gap awaiting the next computation. It is a structural boundary on explanation that may be fundamental. Every framework we have for explaining things presupposes some background context, some prior state, some set of laws, some space of possibilities within which events occur. The question of why any background context exists at all, why there are any laws, why there is any space of possibilities, this question has no framework within which to address it. It is the question at the absolute terminus of inquiry, where the chain of explanation ends not in an answer, but in the recognition that there is nothing further to appeal to. Consider what this entire investigation has established. The cosmos runs on physical constants appearing calibrated for complexity. The calibration cannot be derived from any deeper theory. Several serious accounts have been proposed. Deeper physical law making the constants necessary. Selection through universal. Reproduction via black holes. Selection through anthropic observation within a vast ensemble. None is confirmed. All remain in active scientific contention. The constants are what they are, and their particular values are interconnected. The same values permitting stars also permit chemistry, also permit planets, also permit life. The network of constraints is simultaneously satisfied in a way enabling everything interesting to occur. And the probability of this arising by chance is, by any candid assessment, effectively zero. The cosmos has a life cycle. It began in a hot, dense, extraordinarily ordered state. It expanded and cooled. The first structures formed. The first stars burned and perished, seeding the cosmos with heavy elements. Successive generations of stars built on this chemical inheritance, producing progressively more complex molecular environments. Planets formed around stable stars and provided surfaces where chemistry could advance in liquid water across geological time. Eventually, self-replicating chemistry emerged. Life evolved. Nervous systems developed. Minds arose. The cosmos became, in some of its regions, self-aware. The cosmic web, the large-scale structure of the universe, organizes itself according to the same network principles governing neural tissue. The same mathematical rules of network formation manifest across scales from neurons to galaxy clusters. The fine-tuning that permits stars also permits chemistry, also permits minds. The constants are not independently calibrated for physics and independently calibrated for biology. They constitute a unified set of values, enabling the entire cascade of emergence from hydrogen to consciousness. Dark matter provides the scaffolding from which all structure assembles. Dark energy governs the expansion that determines the cosmos's long-term destiny. Both remain uncharacterized in their fundamental nature. The dominant constituents of the universe, the forces determining its large scale, architecture, and eventual fate, are mysteries. What we do know, the 5% that is ordinary matter, the atoms and chemistry and stars, has proven sufficient to produce us. The 95% we do not understand constitutes the context in which we exist, shaping the cosmos we inhabit while remaining beyond our ability to identify. What converges from all these threads is a portrait of a cosmos that is at minimum extraordinarily well suited for the emergence of complexity. Whether this suitability results from natural selection acting on a population of reproducing universes, from anthropic selection within a landscape of possibilities, or from some deeper physical necessity not yet identified, remains unknown. But the suitability itself is not in question. The cosmos does not merely permit complexity. It generates it at every scale across the entire span of its history. And it has done so in a manner yielding the specific complexity of minds capable of noticing. Everything, you know, was constructed by this cosmos from itself. The atoms in your brain were assembled in stellar cores that perished before the solar system formed. The chemical processes constituting your thoughts operate on physics established in the first seconds after the Big Bang. The specific constants permitting your body to hold together and your neurons to function were either chosen, selected, or mathematically necessitated by mechanisms we do not understand. The consciousness enabling you to ask whether any of this carries meaning is an emergent property of matter that has been organizing itself for 14 billion years, under laws appearing calibrated for precisely this outcome. You are not in the universe. You are the universe in the specific configuration that contemplates itself. The question of whether the cosmos is alive is not a question you are posing from outside. It is the cosmos posing it from within, using the only instruments it possesses for asking questions: the minds. It evolved. The recursion is genuine. The question and the questioner are the same object. And what the questioner has discovered after careful examination is that the cosmos exhibits properties, fine-tuning, self-organization across all scales, the emergence of complexity, the production of self-aware minds, consistent with something more than a mindless accident, but less than anything we yet have a word for. Not life in the biological sense, not consciousness in the human sense, something for which our conceptual vocabulary remains insufficient. The science does not assert that the universe is alive. The science reveals that the cosmos possesses properties that, upon careful examination, raise the question of whether alive is too small a concept. The constants are positioned at values permitting the emergence of complexity through mechanisms remaining genuinely mysterious. The architecture of the cosmos from quantum entanglement to cosmic web exhibits the same organizational principles at every scale. The universe began in an extraordinarily ordered state and has been running through that order ever since, generating in the process an unprecedented diversity of structures, including structures capable of asking why. These facts do not sum to consciousness. They sum to something science is still in the process of characterizing. You are enclosed within this thing. You cannot depart. You cannot observe it from outside. Every thought you entertain about it is a physical process unfolding within it. The enclosure is absolute, but it is not a confinement. It is a membership. You are not trapped within the cosmos. You are part of it, among its most recent and most extraordinary configurations of matter, equipped through billions of years of cosmic and biological evolution to understand something of the whole. The universe has existed for nearly 14 billion years, and has produced in that time everything from quantum fields to consciousness. It will persist for time scales so immense they render the current age a single instant. What it will produce in those vast future expanses remains unknown. What it has produced so far, including you and the capacity to pose the question you are now contemplating, is the most remarkable phenomenon in the observable cosmos. And nobody warned you that the thing you inhabit, the thing you are made of, the thing you belong to, might be doing something that resembles what living things do, might have been doing it since before any star ever ignited, might be doing it still in ways so immense and so gradual that the only instrument sensitive enough to detect it is precisely the kind of mind that a cosmos full of stars and heavy elements eventually constructs. If any of that lingers with you after this video ends, sit with it. Let the question breathe. Because the question of whether the universe is something more than the sum of its physics is not answered by any equation yet written, and the fact that you are now carrying it forward means the investigation is still alive. Subscribe if you want to keep thinking about questions this large, because we are just getting started, and the most important part of any exploration is not the answers you collect, but the quality of the questions you refuse to let go. The question is real. The investigation has just begun. The answer, whatever it is the most important one anyone has ever pursued.